Okay, guys, we're going to get started here with Statistics 10.2, Day 1. We are looking at the sampling distribution for a difference in means. So we'll get that started for you right now. Last year, East Kentwood High School had 30 students take the AP Stats exam. We were informed later that the College Board gave us 2 forms of the exam, which were randomly assigned to the students, and here are their scores. Of course, you can see that, and so your first job here is to figure out, well, what is the mean score for Form A? What was the mean score for the Form B? And then finally, what were the difference in scores? So take a minute to do that. We'll come back with the answers. Well, as you can see, the mean score from Form A was 4.2, and the mean score of Form B was 4.0. Remember, to get those, you just throw those numbers in your calculator and use 1var stats. Finally, the last question here is, what was the difference in means? It was 0.2. Assuming that the 2 forms were the same difficulty, and they should be, if Doug scores a 5 on Form A, then he should also score a 5 on Form B. In other words, our friend Doug is a 5 no matter which form he takes. So the 30 scores from from the class are written on 30 cards. We're going to randomly assign half of the cards to Form A and the other half to Form B. What was the difference in the random assignment? So, in our new school environment where we're doing everything online, we're not able to do this, but I was able to do this using a computer simulation, and here's a clip of that. Okay, so from that, we were able to create our scatter plot, which looks like this. There's our scatter plot, and you're going to notice that the very first one I did was 4.7 and 4.13 for Form B. So let's take a look at that scatter plot unobscured. All right, here's that scatter plot. So how many times was the mean difference 0.2? Well, over here you can see that's 1, 2, 3, 4 times. That happened quite a bit, actually. How many times was it negative? I think this is negative 0.82 or something, 0.83. Well, that only happened 1 time right over here. All right. So if you think back to only a few minutes ago, East Kentwood had a difference of mean scores of 0.2. So we are going to ask the question, is that outcome rare? Okay. Is it surprising if we assume that both forms have the same difficulty? And so what we're going to do is we're going to see, well, how many times in our, admittedly not a very large experiment, but how many times in our experiment did we get a result that was 0.2 points away from, even, with a difference of 0.2 or more. Now remember, that includes negative values, and that also includes positive values. So you got to think, it's got to be greater than 0.2 or less than negative 0.2. So how many times did that happen? And I think you already saw, that's what I highlighted here. This is all the times everything in the highlight is all the experiments that were a mean difference of 0.2 or greater, or negative 0.2 or less. How many times is that? Well, I counted that at 13. That happened 13 out of my 20 experiments. So if we assume that the difficulties were the same, then there's a 65% chance of getting a sample mean of 0.2 or greater purely by chance. Okay? And that may sound familiar to you because that is the set phrase that we use for a p-value, and that's kind of what we're doing here. We're saying how many times is that difference at least 0.2? It's a p-value. So is that do we have convincing evidence that one exam is more difficult than the other? Well, not really. The result is not surprising. Getting a 0.2 difference, which would, you may think of that as the experimental data. When you stack that up against the sampling distribution, which is what we made, or at least part of the sampling distribution, when you stack it up with the sampling distribution, then getting a difference of 0.2 is not rare at all. So we don't have convincing evidence that one form is more difficult than the other. All right, so that was a nice, fun way of getting us to our learning targets, which would be the shape, center, and variability of a sampling distribution x bar 1 minus x bar 2. I'm going to pause it right here, and you can copy that down. So basically, all this stuff is not all that new to you. It should be what you think it is. The shape, of course, that's going to be normal. We always want it to be normal, but it's only going to be normal if both samples follow the conditions of Fluffy, which would be normal. I'm sorry, not normal. I mean, yes, normal, but not yet. The first one is random. So they have to be, both samples need to be random samples of their population. And the second one is both samples need to be less than 10% of their entire population. And of course, normality, which would be if both samples are either, well, for each sample, it either needs to be from an approximately normal distribution, or each sample needs to be from large sample size greater than 30, or each sample needs to have a histogram that is no outlier and reasonably symmetric. Sorry, small adjustment to what I just typed there. So there is those three conditions. The center of the sampling distribution for a difference of means is just the difference of the true means. And the variability, the standard deviation for our measure of variability, that's the square root of the two variances. Notice that we're using sigma 1 and sigma 2. If we were using experimental data, of course, you would change that into S1 and S2, and in which case you would be using the t distribution. Okay, let's take a look at our check your understanding here. The heights of young men follow a normal distribution with a mu equal to 69.3 inches and a standard deviation of 2.8 inches. The heights of young women also follow a normal distribution. Mu women is 64.5 and standard deviation of women is 2.5. Suppose we select independent SRSs of 16 men and 9 women and calculate the mean height, sample mean heights of x bar m and x bar w. So we've got a few things to highlight here. First of all, we know that the men follow a normal distribution. We know the young women follow a normal distribution. So when we subtract them, then we should get a distribution that is also a normal distribution. Next thing to notice is all of the statistics. You've got XM, the MM should be X bar M, and SM right there. And then you also have N of the men, that's 16. And then for the women, you've got the mean of the women, X bar W is 64.5, SW is 2.5, and NW is 9. So the first question, what is the shape of the sampling distribution? We actually just answered that a few seconds ago. That shape is approximately normal because both men and women, the distributions of men's heights and women's heights are both normal. Letter B, find the mean of the sampling distribution. Take a second here and you will realize that all you need to do, the mean of the sampling distribution is just the subtraction of the two mu's. So you get 4.8. Last question here is to calculate and interpret the standard deviation. So the calculate part is the most math that you're going to do today. You're going to add those variances and square root them. So don't forget, you've got the formula way up over here. Take a second to do that, and I'll be right back. Okay. Square root of 2.8 squared on 16 plus 2.5 squared on 9. I hopefully notated that pretty well so you know which one's which. And that's equal to 1.088. So if you have a typical difference in sample means, that's going to vary from the true difference by about 4.8. That's another one of the set phrases to interpret a standard deviation. So that's it, everyone. That is our 10.2 day 1. Hopefully you enjoyed that and get to work. I'll see you later.